Okay, we will look at, in this video we're going to look at 2.7 and 2.8. We'll start off with, this will be just a few seconds, velocity as a vector. Okay, so we've seen position as a vector, we've seen displacement as a vector, but now we also need to see velocity as a vector. And why is velocity a vector? Well, because displacement is a vector. So we know that velocity, Vx, your average velocity, is delta x over delta time, which is your final position minus your initial position over your time. Another way of writing this is to say, well, that is actually my displacement vector over time. Okay, so straightforward. It is the change in position over change in time. That's what my average velocity is. Now if we move on to 2.8, just rewriting this, your velocity is delta x over delta t. So what we're saying here is that if we're looking, well, motion as a constant velocity, we'll have a look at that now. If we're looking at a position time curve, then we can see that the velocity is equal to the change in the position, this is the vertical direction, over the change in time. Okay, and what is that? That's effectively the gradient of the position time curve gives you the velocity or the slope. So what we can see here is that the slope of the position time curve gives us the velocity. So the slope of the position time curve gives us the velocity, or in a mathematical way, the change in x over change in time gives us the velocity. So if we've got, say, a position time curve here, and we want to draw a velocity time curve, say now we have something that looks like this, say that's your position, okay, then how would you draw the velocity time curve? Well, you would say, well, let's pick this point and let's find the slope there. The slope is quite positive, so we're going to have a very positive velocity. Let's pick a point there, right? The slope is positive, but it's less positive, so at that point we're going to have this, we're going to have a velocity that's slightly less. And what's happening at this point? Well, we know that at this point the slope is 0, so at this point our velocity is 0, so it looks like the velocity is just decreasing and decreasing. So here you're going to have a negative slope, here you're going to have a more negative slope, and that means a negative velocity. Okay, so sorry for the terrible diagrams, but you need to get the idea that if I've got a position time curve and I want to draw the velocity time curve, I need to calculate the slope, and that becomes then the velocity time. So here the slope is positive. It's a positive slope for the position time, so I have a positive velocity. Now, if you move from position time to velocity time, you have to calculate the slope or whatever, or the gradient. If you want to move from velocity time to position time, then you need to calculate the area under the curve between those two times. So let's have a look here. Remember what we said was that velocity is delta x over delta t. So if I'm moving from, if I've got my position time and I want velocity, I need to calculate the slope. However, let's rearrange this so that it looks like this. Remember that this is x final minus x initial over delta t, right? So if we rewrite this, let's just get some more space here. Okay, so if we rewrite this, then we see that x final minus x initial is equal to v times delta time. Okay, so I've just rewritten this, and this is what we get. So remember, if you've got position time, you get the velocity by calculating the slope. But if you've got velocity time like this, and you want to calculate or construct the position time curve, we can use this. So essentially, if we are given, say in this example, we're given the initial position. Say there's your initial position. Let's write. There's your initial position, xi, but we want to find what is our final position. What is our final position? Then we essentially take the velocity and multiply it by the delta t, which is essentially to calculate the area under the velocity time curve. So I have my initial position. I'm trying to find my final position. So I need to calculate the area under the curve. So I multiply my velocity, Vx, times, so that is this height, that's my Vx, and then delta t is the breadth. So here's the height times the breadth, that's the area under the curve. So what we're trying to say here is that the change in position is equal to the area under the curve. The change in position is the area under curve. So how I move from initial position to final position is the area under the curve. So that change there, that change from x initial to x final is equal to this area under the curve. Okay, I hope I didn't confuse you too much. See you in the next video.